Hello, this is the team Mission Impossible for the Direct Air Capture Project for ChemE Cube. My name is Isaac Camp,
I'm Mark Hour.
I'm Lucas Edwards. And I'm Michael Maloney.
and our professor and advisor is Patrick.
All right. So a quick slide overview. We're going to be addressing the problem. We're going to briefly discuss marketing, the cube design, and potential safeties. Starting off with our problem, CO2 accounts for approximately 80% of all greenhouse gas emissions and has risen over 100 parts per million over the last 70 years. Many companies have taken multiple attempts to reduce CO2 emissions by using renewable energy sources, and just trying to drive less, carpooling, stuff like that, making more efficient cars and houses, stuff like that. And we intend on utilizing these to create a carbon capture device that will help us capture carbon, but it has a high energy cost. So we're going to use a direct air capture device, or DAC, to convert atmospheric CO2 into a storable gas within the project design specifications. Our DAC must fit within a 1 foot by 1 foot cube and must cost less than $2,500. We're going to optimize the CO2 capture with accounting for multiple factors such as energy consumption and the weight of the cube, and then we'll provide a marketable solution and design for this problem.
As Mark was saying, the biggest economical constraint for this issue is the energy cost of boiling the CO2 out of the solvent. That is mainly due to it being water-based solvents aqueous, which we are looking at non-water-based solvents. Other methods for carbon capture include solid media and membrane, but we're not looking at those for uh, multiple reasons. Liquid state seems to be the most efficient in terms of energy consumption.
So our cube design, as said by Michael, is utilizing a non-aqueous solution for the absorption process due to lower recovery energy, which was a major cost driver in main manufacturing scenes. Our main absorber tower will involve a packed bed to increase mass transfer surface area, and our solvent will go through a heat exchanger to preheat and cool down in intermediate stages, which will be seen shortly. And the recovery tower will use an electric heater along with the recirculation to provide mixing, and it'll be under a slight vacuum to help CO2 desorption. Our solution will be fed and cooled by either inlet air or other cooling devices, which is up in decision right now. And we will be using Aspen HYSYS to optimize flow rates and preliminary design sizings for our overall design. So as stated earlier, here's a short process flow diagram where air is fed into a heat exchanger and into the absorber by either a sparger or direct air intake. And our solvent is going to be coming at the top, coming through the packed bed, going through the bottom pump, where a heat exchanger will preheat with already recovery tower solvent. And solvent will be circulated through that heater on the side onto the right of it, while CO2 vapor will be pulled out by that vacuum pump. And recovery tower solvent will then go through the heat exchanger to be pre-cooled before being cooled finally to operation temperature by air.
The safety will mostly revolve around the amines that are going to be used. The cube bottom will be sealed to contain any potential liquid spill to only the cube area, such that we don't have a widespread spill cleanup. Thermocouples will be in place to monitor solvent temperature, especially since this is a sealed system. That'll be critical to prevent overpressurization. And in addition, pressure relief valves will be there to avoid the negative pressure pitfalls since we'll be using a vacuum. Personal PPE will always be used during the design. That will include, in this case, safety glasses, lab coat, nitrite gloves, and chemical gloves, depending on amines and solvents being used, and a face mask and apron when directly pouring said chemicals. The amine solutions will be treated as aqueous waste and thus will be disposed of in a dedicated aqueous waste container after trials. However, during trials, since we are planning, there will be a recycle stream of the amine solution that can be heated to remove the CO2 and ran back through the system to recollect. So for the finalized design, the goal is to have very little actual waste amine during runtimes. Continuing on to safety, amines and amine solutions are known to cause irritation to the skin, eyes, and respiratory system, and some are also potentially flammable and possess carcinogen risks depending on what we're using. All handling of amines will be done within a fume hood, knowing this with the proper PPE as stated prior, until they are safely sealed within the design, and even then, especially during early stages, that will most likely still be conducted in the fume hood. SDS sheets are going to be shown later for links, but known chemicals that we will probably be pursuing include ethanol, DI water, 1,2-dimethylimidozine, ethylene, diethylene solution, and other potential amines are still on the table at this stage as we pursue non-aqueous amine usage, but the predominant choices are most likely the ones above. Here you can see our sources. Give a sec just to look at those. And then material SDSs can also be seen here. This is our current virtual submission for the ChemE Cube competition, and we look forward to hearing about any potential commentary. Thank you.
Thank you.
Thank you.
Yes.
Okay.
Cool.
Now I got to figure out where that's stored.
The classic.
Did you do it over Zoom?
I did do it over Zoom.
Okay, it's you gotta give it a minute after you have to end the meeting
Okay.
and then give it a minute. It'll go to your Zoom cloud and then you